Right, good evening once again. We are now moving on to capacitance. Today we want to look at capacitance. So these are the key points that we need to look at. So by the end of this lesson, you should be able to define capacitance and its unit as the farad for any isolated conductors and parallel plate capacitors. And you also need to recall and use that capacitance is equals to charge over the voltage. We also need to derive and use the formula for capacitance of capacitors connected in series. You also need to derive and use the formula for capacitance which are also connected in parallel, and we need to deduce that from the area under the potential charge graph we can obtain the equation, that is the energy stored in a capacitor is half a charge times the voltage, or half of capacitance times the voltage squared. And you also need to understand some functions of capacitors in simple circuits, right? So we can move on to parallel plate capacitor. So here is the symbol for a capacitor. This one, it represents the symbol of a capacitor, and it will be a parallel plate capacitor. So generally we are saying capacitors are devices used for storing charge and energy in electrical circuits. So that's the main function of a capacitor. We are saying these are electrical devices that are used to store charge and energy in electrical circuits. They usually consist of two metal plates a short distance apart, separated by an insulating material. So usually we are saying there is a material between those two plates which is an insulator. Maybe between these two parallel plates we put a what? An insulator. So separated by an insulator, right? So we are saying in the circuit above, when this switch is being closed, we are going to see the electrons which are going to flow from the negative terminal. So electrons, they are going to flow from this negative terminal in this direction into the left hand plate. This one is the plate of the capacitor, and an equal number of electrons will leave the right hand plate and move to the positive terminal. The left hand plate is then a negative charge. This left hand plate is going to have a negative charge, and the right hand plate will have an equal and opposite charge, that is the positive charge. So the net charge stored in the capacitor is 0. The net charge being stored in this is 0, because if we have this plus this, we are going to say it's 0, right? Then we have this relationship between voltage and charge. We are saying the greater the voltage that we have, the greater the voltage V, the potential difference across the capacitor, the greater the charge. So this one is our expression. We are simply saying charge is directly proportional to the voltage, and that is doubling V will also double Q. So for proportion, if you remove the proportional sign, you're going to see that your Q charge is going to be a constant, K times V, and we are saying that constant is what we are referring to the capacitance. So the capacitance is going to be the constant when charge is directly proportional to the voltage. So where is the capacitance of the capacitor? So the units of the capacitance are the farads, usually denoted by F. So capacitance is the charge stored per unit potential difference. So this one is the definition for capacitance. And capacitance C of a capacitor is the charge stored per unit potential difference. So meaning to say, if we are to make our capacitance the subject, we are going to have our capacitance is equals to charge per voltage. So one may ask, what are the SI units of capacitance? SI units of capacitance. So we are going to have charge over voltage. So our SI units for charge, remember that charge is also a derived unit, which is equals to current times. Charge is also current times time. So that's why we are having the units for A, which is amperes per second. And also remember voltage, it's work done by charge. So remember voltage is work done by charge, meaning to say the unit for voltage, it will be joules per coulomb. Please don't confuse yourself with this C and this C. This C here is for capacitance and this C here is for coulombs. But again, we want the SI. Joules, it's for work done, and remember work done is force times distance, meaning to say force is MA, we say that is kg, meter squared, s power of minus 2. Then for the coulomb, we are going to say it's 8 power of minus 1 times 8 minus 1. That is, we are expressing everything in terms of SI units. So finally, so I need you to get a pen and paper, then simplify. We are going to get our SI units as this one. That is, we are going to further divide joules into SI units. Joules is work done. Work done is force times distance, and your force is equals to MA, mass, which is in kg, A, which is meters per second squared. Then the distance also going to multiply with another meter. That's why we are having this meter squared. So finally we get this one as the SI unit. Now moving on, if we can move on, right, we can move on. So we are saying most capacitors has capacitance that have got very that are very smaller than 1 farad. So in this table, as you can see, we have got microfarads, which are represented by this prefix, that is 10 times 10 to the power of minus 6 farads. We also have nanofarads that have a prefix of n, that is 10 to the power of minus 9 farads. Then we have picofarads, that is 10 to the power of minus 12 farads. Like what I have indicated earlier, that you must not confuse yourself with this symbol C and the other symbol for capacitance, like what we are seeing here, right? We have this worked example number 1. Is saying what? We have a 500 nanofarad capacitor connected to a 12 volts DC supply. What is the charge on either of the plate of the capacitor? So from our definition, charge is equals to capacitance times voltage. Our capacitance is 500. Must able to convert the nanofarads to 10 to the power of minus 9. Then we are going to multiply with our voltage, which is 12. Then we are going to get our charge is 6 micro coulombs. Moving on to example number 2. As you can see, a potential difference of 5 kilovolts is connected across a 470 microfarads capacitor. What is the charge stored? Again, using the same formula, charge stored, it's a capacitance, that is the 470 times 10 to the power minus 6 for micro, times our voltage, which is 5 kilovolts. So we are going to express in terms of volts, then we're going to get 2.3 coulombs. Then if you read B saying how many extra electrons are there on the negative plate of the capacitor, and you are giving this value, that is the charge for each electron. So if you want to find the number, remember from DC, from current, remember that charge is equals to like in this case, charge is equals to CV. But remember, when you say, we can divide this charge as the total number of electrons that we have times the charge of each electron. So meaning to say, here is our charge 235. We're going to say our 235 here is equals to our Ne, the number of electrons times the charge of each electron. So here, if you want to find the number of electrons, you're going to say number of electrons is equals to 235 over the E that we are having here. So hence, if you look at this example, you are going to see that the number of electrons will be 1.47 times 10 to the power of 19. Those are the electrons that we have. So before we move on, you need to take note of this point. If we have a capacitance of 2.35, which means that the negative plate will be plus 2.35 of capacity of coulombs, and the negative plate will be minus 2.34 coulombs of the charge on the other plate. Now we want to look at capacitors in series. When capacitors are connected in series, like in our diagram fig 18.4, we have a capacitor 1, capacitor 2, capacitor 3, and their charges. So across this capacitor we have a voltage V1, here V2, and here V3. Right, as you can see from the Kirchhoff second law, where we say the total of EMF is equals to the total of PDs across the circuit. So this voltage, the supplied voltage, will be the same as saying V1 plus V2 plus V3. And from our definition, what do we know? From our definition, we know that V is equals to charge over voltage. That's why we are now expressing V1 in terms of this formula. It will be like Q1, it's like the charge over C1 plus charge over C2 plus charge over C3. And why are we saying the charge is the same? Because here, as you can see from the diagram, we have the same current moving through this one and this one and this one, the same current. If we have the same current, we will have the same charge. We are going to have the same charge. So if we are to factor out, like here we have that charge over the total capacitance that we we are looking at. So if we are going to factor out charge, like, or if we are going to divide throughout all the charges, if we cancel this charge and this charge, we are going to remain with this expression like this: 1 over charge total is equals to 1 over a capacitance 1 plus capacitance 2 plus capacitance 3. Remember this formula in DC circuits, whereby we are saying this capacitors add up in series in the same way as resistors add up in parallel. So finally, if adding capacitors in series, it makes the capacitor with a small capacitance. The capacitance will be small. So it's another way. If you want to make a small capacitance, you have to put your capacitors in series in order to decrease the capacitance. Right, moving on to this worked example: 3 capacitors with capacitors 3 microfarads, 4 microfarads and 5 microfarads are connected in series. What are their combined? As you can see, we're going to say 1 over combined is equals to 1 over 3 plus 1 over 4 plus 1 over 5. In mind, we are ignoring the prefix because we're going to say our final answer will be in microfarads. Like this here, I forgot to put this microfarads. That would be your final, meaning to say 1 over combined is 1/3 plus that. Then you have to change this one, find the common denominator, then you take this one, you're going to get a 1.3 microfarad. On example number 2, we have a 5 microfarad capacitor is connected in series with a 10 microfarad capacitor. The combination of the capacitor is connected to a 12 voltage DC supply. As you can see in this diagram, we have this capacitance and this capacitance connected to this. Calculate the PD across this 10, this V2, and also want to find the charge stored on this capacitor. Again, from Kirchhoff's second law, if we add this voltage 1 and a voltage 2, it is going to give you the total voltage of 12 volts, like in this equation. So meaning to say, charge on both capacitor is the same. Why? Because current is flowing through, is the circuit is the same. So charge is given by capacitance over volt. So we are going to say capacitance for this one in terms of charge. We are going to say if the charge is the same, meaning to say charge on this one, and the charge on this one is capacitance 1 times V1 here, it will be the same as capacitance here 2 times V2. That's why we are seeing this. Our capacitance, the first capacitance, this one times V1 is equals to this one times this. Then we are going to say, we're going to come up with the V1 is equals to 2V2. That's equation number 2. So this, remember our first equation and remember our second equation. So from equation 1, we are going to see that if we are going to solve equation 1 and equation 2, we're going to see that V1 is 8 volts, then V2 it's 4 volts. That is solving equation 1 and equation 2. Where are we getting this one? Like if you take equation 1 where there's V1 and substitute V2, we are going to see that we are going to have 2v2 plus v2 is equals to 12. And if we add here, we are going to get 3v2 is equals to 12, and then you divide by 3. That's why we are saying our v2 is it's 4. Then if you the back substitute here, you would see that v voltage is equals to 8 volts. So across the 10 v2, our v2 will be equals to 4 volts. Then the charge on the 5 micro capacitor, again you are going to use this one. So it's the charge on this one times this v1, which is 8. So we are going to have the 40 micro coulombs being stored there. Now looking at the capacitor in parallel, like in this diagram, we have a capacitance connected in this. So whenever we connect resistors or capacitors in parallel, we are going to have the same voltage here. The voltage across this, it will be the same as this V. So the total charge being stored here, as you can see, we are going to have current in this direction. This current, let me say this current is I. So this current is going to reach this junction. We are going to have current 1 being divided here. Then some part of the current will go here, and to split here again, we are going to have another current, what? Current 2. Then obvious the remaining we will go through this one, and we have our current 3. So meaning to say, charge, total charge will be charge, flow of this. Remember, current is flow of charge. We are going to say flow of this charge plus flow of this charge plus flow of this charge. Then we come up with this equation, the total charge stored. But remember, from our formulas, charge is equals to capacitance times voltage. So charge at 1 here is capacitance 1 times the voltage, which is the same throughout, plus capacitance 2 times voltage plus capacitance 3 times voltage. Then if we are to factor out V, which is the same here, if you are to factor out V here, we're going to remain with capacitance 1 plus capacitance 2 plus capacitance 3. Then if we divide both sides by V, V goes here, we have Q over V, which is the final, the combined effect of the capacitance in parallel. So that will be capacitance 1 plus capacitance 2 plus capacitance 3. So that is the combined effect of the capacitor in parallel, just add the capacitors. And remember, the same way capacitors add up in parallel is the same way as resistance add up to in series. Remember, resistance in series, it's R1 plus R2. So meaning to say, adding up capacitors in parallel makes the capacitor with large capacitance. So likewise, in an exam they may ask you, how can you make a large capacitor if you are given maybe 3 or 4 capacitors? So you need to connect those capacitors in parallel. And if you want smaller capacitance, you have to connect the capacitors in series, like what I've indicated earlier. Moving on, you can see this worked example here. Example number 1. 3 capacitors of capacitance 1000 microfarads, the other one 2200 microfarad, and the other one 4700 microfarads are connected in parallel. What are the total effective capacitance? So if they're in parallel, we're simply adding the 3 and you get your 7900 microfarads. Then part B, if the parallel combination capacitance is connected to a 12 volts supply, power supply, what's the total charge? So this one we are going to use total charge is equals to the combined capacitance, the one we have calculated here. Remember to change the micro to 10 to the power of minus 6, then multiply with the voltage, and we are going to get, what's this? It's 95 millicoulombs. Then on question number 2, 3 capacitors are connected as shown in this diagram. We have these 3 capacitors. The total effective capacitor is 20 microfarad. What is the value of this capacitance? So as you can see here, these two, they are connected parallel, so the total here to be 60. We add here and here to be 60, but these two now, they are connected in series. It's like I'm saying the total for this is 60 microfarad, because they're in parallel. If they're in parallel, just add. Then we also have this. So this one is like we have 60 microfarads, and this one we have. So if they are now in series, we are going to say the effective that we are given 1 over combined, which is 20, is the same as 1 over 60 plus 1 over c. That's why we are having this equation. It's similar, because this 60 is coming from adding this, because they are in parallel. So if they are in parallel, just add. But this one and this one, they are not in series. How are we going to say? We are saying 1 over the combined, which is this one, the combined, the total, is equals to 1 over 60 plus 1 over c. Then you make your c the subject. You would find that your c is going to be 30 microfarads. Now we want to look at the energy stored in capacitors. When a capacitor is being charged, work is done in pushing the charge onto one plate and pulling it off the plate. So for a capacitor that is initially uncharged, the work done in pushing the first few charges onto other is very small. But if as the charge on the plates build up, it gets harder and harder to push more charge onto the plate, because charges already are repelling to each other. Like if you have a plate, these two plates, and if we are charging here, suppose this plate is negative, already we have a negatively charged, and if we are charging again, you can see that we'll be trying to force these charges on this plate. Mean to say these are negative and these are negative, there will be a repulsive force. So that work done in overcoming that force is what we are referring to the energy stored in a capacitor. So the energy stored in a capacitor W, charged to a potential difference V, is equal to the area under the graph, like this one. If we are to plot the voltage here and charge here, this shaded area represents the energy stored in a capacitor. In an exam, they may give you this this diagram and say shade the region represent the energy stored in a capacitor. They will just twist, they will put charge here and put voltage here. So remember, its area over under the PD charge graph, so it will be this region. So make sure to identify your x-axis and your y-axis. If your x-axis is charge and your y-axis is voltage, then this one will be the area. But if we happen to twist the graph, you see that the area will be the shaded ones. So make sure to note that. So area under the graph is half base times height. So our base is Q, our height is V. That's why we are seeing this formula. It's half base times height, half QV. But now using this formula, we can eliminate Q, where this Q subject to the CV. So your equation will be half CV squared as the total. Because here already we are saying we have half, and what is our Q? It's CV times, already we have this V, and if you multiply the two, we are going to get this expression finally. Then we can look at the uses of capacitors. Capacitors have a wide range of uses in different letters, in flash photography and backup power supplies for devices such as computers. They are used as backups. So you can also find more examples on the uses of capacitors. They are used as gap up, maybe if we have a shortfall in, as you can see, sometimes still remember when we have some lights that uses capacitors. When these are gone, you can see some lights will remain on, because when the light is on, when there is sensor, it will be charging the light with its capacitors and again with some batteries inside. So there will be a combination of batteries and capacitors. So when the Zs are gone, then it will be discharging, then the light will continue lighting even though we have no electricity. So it's some uses of capacitors. And we also have this worked example. We have also this graph. This graph shows the charge on a capacitor is the potential difference across it gradually increases. As you can see here, we have a capacitance from this one to this one. Now what is the capacitance? The question is saying what is the capacitance of the capacitor? And you know, capacitance is Q charge over V. So we are going to say charge at any point, the point that you can easily found. Like here they are using this 12 and our voltage, you can take voltage is 12 or even at 6. We can take 12 and see where the charge is going to be, where it cuts here and goes here. So you can see our charge will be 240 microfarads. So since capacitance was charge over V, we're going to say it's that charge, that 240 times 10 power of minus 10 divided by the voltage, which is 12, and we are going to get the capacitance is roughly 20 microfarads. So even you can take at this point 6, you can say 6, and if you add 6 you can get 120, mean to say the energy stored will be half C V squared, and since we have found the value of C, we're going to say it's half, and our C here, the one we've calculated capacitance, times the voltage, because they are saying what is the energy stored when the voltage is 40, then times 14, and we are going to have this one as the answer. Then part C now is saying the capacitor is partially discharged, so that the PD across it falls from 14 volts to 9 volts. How much energy is lost? So we are going to see if the capacitor is discharging. Let me try to erase this one. Let me try to erase. Remember, we have said area energy stored is area under which is area under this graph. It's area under the charge, the voltage charge graph, and if you have this charge to the y-axis and voltage to the that one, like what we have, this area will represent the energy stored. Charge on the, as you can see, if the charge is on the y-axis and voltage here, this area will represent the energy stored. So we want to find how much energy is lost from 14 to 9. Like here we have this 14, and they want to see what's the charge. This charge will be 280. So it decreased 14 to 9. Again for 9, somewhere at 180. So our area will be, what will be our area here? I'll try to highlight this one. Failing to highlight. It's okay, fine. So this one will be our area, required area here. That is the area of the trapezium. So we are going to say our area of a trapezium is half, where we are going to add, this one is our A, we are going to add 9 plus what, 14. Then what is going to be our height? Our height, that will be 280 micro, so it's 280 microfarads minus what? Minus 180. That's the height, 180 microfarads. Then if you calculate this one, you find the same answer as the one below. So that will be the area. Then on number 2 now, we have this defibrillator. See the diagram. A device provides an electric shock of heat. That one, a capacitor of 15 microfarad is first charged to the potential difference of 8 kilovolts. It is then discharged through the patient using two metal discs connected to the insulated. Calculate the charge on either the plates. Our charge, we are given capacitance and the voltage, and our capacitance is 15 microfarads. Then our voltage is 8, so we just punch and multiply, get this one, Energy stored again is half CV squared, so it's half our C capacitance, that's 15 times 10 to the power minus 6 times the voltage, which is 8000 squared. Then get this one. So I think for you can pause this video and read question number 3, and if you read your question number 3, so you can pause, then try to work on your own, and after that here will be your answer. Make sure to see if it is your answer, if you are able to get this. If you are able to get this, if you have paused, here is going to be your answer for number 3. That will be your answer. So thank you for watching. I think the lesson has helped you. We have tried to cover all the points here that we were looking at under capacitance. You are now able to define capacitance, and we are now able to define the farad, to derive the capacitance of capacitors in series, in parallel, and also use that formula to find the area under the graph, and also understand the function of capacitors in different circuits. So for now we can end here. Have a good night.